In the last video, we talked about how you can use the first derivative to classify maximum and minimum values for a function. So specifically, the sign of the first derivative will tell us where a function is increasing and where it's decreasing, and the locations in the middle where we transition from one behavior to another represent what we call critical values. So depending on what we see to the left and the right of a critical value, that will tell us whether that value represents a maximum, a minimum, or neither in relation to the points around it. So far we're really only talking about relative extreme values, which just means extreme, highest, lowest in relation to the points around it. In this video, we're going to talk about how you can use not only the first derivative to classify extreme values, but also the second derivative, which remember the second derivative is just the derivative of the first derivative. So if you take a function and differentiate it twice, you get the second derivative. So when we talk about first derivatives give us information about where a function is increasing and decreasing. Second derivatives, are going to give us information about a function's concavity, and I'll explain what that term means in just a second. Okay, so in general, the first derivative tells us how the original function is changing. So remember, the original definition of the derivative is it represents the slope of the tangent line at a particular location. The tangent line, the slope, represents the instantaneous rate of change of that function at that one specific location. So the derivative, the slope of the tangent line, tells us how the function is changing at a specific point based on a particular x value within its domain. The second derivative, on the other hand, tells us how the first derivative is changing. It's the rate of change of the rate of change, if you want to think of it that way. So what could we determine based on a graph, based on what we're seeing about the first derivative? So suppose this is the graph, little snippet of a graph of a function. We want to look at the tangent lines at two locations. So here's one location, and we've drawn the tangent line at those two locations. Well, we know at the first location, the tangent line has a negative slope, so we would say that the function is decreasing at that particular location. At the next location, the tangent line has a positive slope, which means the function is increasing. Okay. What we can also say, though, in terms of comparing the derivatives, is that we're going from a negative derivative to a positive derivative, which means the derivative itself is increasing. The rate of change of the derivative is positive. We're going from a smaller derivative to a larger derivative, a more negative derivative to a more positive derivative. Well, if the second derivative tells us how the first derivative is changing, then this idea that the first derivative is getting bigger means that the second derivative is positive. The second derivative being positive tells us that the first derivative is increasing. It's going from smaller values, in this case a negative value, to larger values, in this case a positive value. Now we could also potentially have a graph that looks like this. And again, we're comparing what's happening at two locations. So suppose these are the two locations we're looking at. And again, we've drawn the tangent line at each of those locations. At the first x value, our tangent has a positive slope. And at the second x value, our tangent has a negative slope. So that means we're going from a positive slope to a negative slope. That means our derivative, the slope of the tangent line, is decreasing as we transition from one x value to another x value. So what that tells us is that the second derivative is negative. Again, if the derivative represents the rate of change of the previous function, then the second derivative tells us how the first derivative is changing. If the second derivative is negative, that tells us the first derivative is getting smaller. The rate of change is negative, so it's going down. Okay, so changes in the first derivative correspond to changes in the bending of the graph. That's what we can see from these two graphs. If we were to look at the two tangent lines at each of these locations, the fact that we go from a negative tangent to a positive tangent means there's a bend in the graph. So if you were to graph a bunch of tangent lines, essentially you're tracing out the basic bend in the graph. And same thing over here. We go from a positive slope to a negative slope, which corresponds to a particular bend in how the graph curves. This idea of how the graph bends, bending like this versus bending like this is what we call concavity. So the concavity of a graph is just the shape of its bend. In other words, are we bending downward? Are we bending upward? That's what we call concavity. So we can determine concavity from the second derivative of a function. So if the second derivative of our function is greater than 0, that means the first derivative is increasing. So remember, a derivative is a rate of change. The second derivative is the rate of change of the first derivative. So if the second derivative is greater than 0, that means the rate of change of the first derivative is a positive number. It means the first derivative is getting bigger, it's increasing. If this is the case, then this is the general shape that we have. And we call this shape upward concavity. So in that case, the graph is what we say concave up. We would classify this portion of this graph as being concave up. Now, if the second derivative is negative, if it's less than 0, that means our first derivative is increasing. Again, if this is a rate of change, the second derivative tells us how the first derivative is changing. Well, if the rate of change is less than 0, it's negative, that means that the first derivative is getting smaller. We're going from a positive slope to a negative slope, so our slope is getting smaller. And again, it corresponds to this kind of shape based on what we're seeing with those first derivatives. So in this case, we would say we have downward concavity. In other words, the graph is concave down. Now, how do you remember which is which in terms of the shape? Here's how I remember it. I remember that it is up like a cup and down like a frown. So upward concavity, shaped like a cup, downward concavity, shaped like a frown. So it rhymes, and so hopefully that'll help you remember which one is which. So anytime the second derivative is positive, we're concave up, up like a cup. Anytime the second derivative is negative, we're concave down, down like a frown. And so again, that gives us a general shape for the graph in terms of how the graph is curved. Now we have to be careful about this idea of concavity and comparing it to what we know about where the function is increasing and decreasing, what we determined from the first derivative. We have to keep in mind that these concepts are separate from one another. In other words, we can have different combinations where our function can be concave up and either increasing or decreasing, and concave down and either increasing or decreasing. We have a bunch of different things we can see, and we have to keep in mind that these two ways of classifying a function and classifying its graph, they are independent of one another. So suppose our first derivative is negative. If our first derivative is negative, that means we are decreasing, and that's what we determined from the last video. When we talked about increasing and decreasing, anytime the first derivative is negative, we're decreasing. Now, anytime the first derivative is positive, we are increasing. Now, if the second derivative is negative, that tells us that we are concave down. Concave down. Down like a frown, and I'm about to draw it the wrong way. Concave down. There we go. We've got something shaped like that. Anytime the second derivative is positive, we are concave up, up like a cup. So how would that combine with something being increasing or decreasing across a particular interval for our function? Well, if our graph is concave down and decreasing, it means we have something like that in terms of the shape of our graph. So concave down, down like a frown, and also decreasing means we have something like that. Now, if it's decreasing, but it's concave up, it has to be sloped downward, but sloped downward with this kind of curvature. So imagine just taking the downward sloped portion of this particular curve, which would be something like that. That would be decreasing, but concave up. Now, what if we're increasing, but concave down? Well, that would be the increasing portion of this shape. So we're increasing, but we're curved downward, we're concave down. And then increasing, but concave up would look like the other portion of this curve. So increasing, sloped upward, concave up, sloped up like a cup. So we do need to be careful in differentiating these two concepts. The first derivative means one thing, the second derivative means another thing. We can analyze each independently, and depending upon the combinations we see for what's happening with the first or the second derivative, we have different indications of what the graph would be doing for our particular function. So now let's talk about what we call the second derivative test. The idea is that we want to use these concepts, again, in order to classify maximum and minimum values and to give us a sense of what a graph might be shaped like. So concavity also gives us information about relative extrema. So specifically, just like with the first derivative test, it gives us information about whether specific values could represent a maximum or whether they would represent a minimum, or possibly neither. Remember, we saw specific values that were special in a sense, but somehow they didn't represent a maximum or a minimum based on what we saw about the first derivative. So here's the second derivative test. Now we're going to start out the way we started the first derivative test. So the idea of a critical value, we're still going to apply that concept. So our relative extreme values still occur at critical values, and the term critical value still means the same thing. So remember, critical value means it's a location where our function's derivative is either equal to 0 or undefined. Now, if we're going to use the second derivative, we have to limit our definition of a critical value. So suppose our function has a critical value at this particular value of x, but specifically, we want situations where the function's derivative at that particular location is 0. So we're excluding the situations where we have a critical value, but it was associated with a location where our function was not differentiable, where the function was undefined. If it's undefined, then if the first derivative doesn't exist, we're going to find that the second derivative doesn't exist as well, and we're not going to be able to use the second derivative test. So here's what the second derivative test tells us. It tells us that the function value for that critical value, the actual y value, the actual output, it tells us that it is a relative maximum if, and this is going to seem counterintuitive, if our second derivative is negative. It's a relative maximum if the second derivative is negative. I'll explain why in just a minute. The function value associated with that critical value represents a relative minimum if, again, counterintuitively, the value of the second derivative is positive at that location. Well, normally we would think negative would make something small, it would minimize something, and positive would make something large, it would maximize something. Why is that not the case here? Well, we have to think about what the shapes are for the graphs corresponding to these values of the second derivative. So let's flip back over. What does it mean for the second derivative to be negative? What does it mean for the second derivative to be positive? If the second derivative is negative, that means our graph is concave down. Remember, down like a frown. So the second derivative is negative, tells us that our graph is concave down. Well, if this is our critical value and our graph is concave down at that location, well, that represents a maximum. That's the highest point in relation to the points around it, just based on how the graph would curve at that particular location. Now, if our second derivative is greater than 0, remember that means that our graph is concave up. up like a cup, down like a frown, up like a cup. So if our graph at the location of our critical value is concave up like a cup, then that means the critical value represents the location for a minimum. Because again, based on the curvature of the graph, we would have a valley at that particular location. So we're looking for the same x values. We're still looking for those critical values. We're just classifying them in a different way. So we're not using this concept of increasing and decreasing, where we sloped upward, where we sloped downward. We're analyzing what's happening at that specific location. So at that specific location, either our second derivative is less than 0, our second derivative is greater than 0, which indicates a particular type of curvature for the graph. And based upon the curvature, either we've hit a peak, which represents a relative maximum, or we've hit a valley, which represents a relative minimum. So let's do a couple examples applying the second derivative test to find our relative extreme values. So again, we'll find the critical values the same way we did before using the first derivative, but now we're going to classify them using the second derivative. Okay. So we want to use the second derivative test to find all of the relative extrema, in other words, maximum and minimum values, for the function f of x is equal to x cubed plus 3x squared minus 9x minus 13. And then again, we want to sketch the graph using our graphing calculator. Okay, so for our critical values, remember that means the same thing. We're looking for locations where our derivative is 0 or undefined. Now again, if we're going to use the second derivative test, we can't include those locations where the first derivative is undefined, because the second derivative will be undefined as well, and we won't be able to apply these two criteria in order to determine which case we fall under. If f prime of x or f double prime doesn't exist, then it's neither less than 0 or greater than 0, so that's not going to apply. So specifically, we're just looking at the locations where our derivative is equal to 0. So we need to start by finding our first derivative for our function in order to find those critical values. So we're differentiating our function. So that's going to be 3x squared plus 6x minus 9. So our critical values are going to come from setting that equal to 0. Now, because we're going to use the second derivative test, let's go ahead and find the second derivative as well. So the second derivative results from differentiating the first derivative as a standalone function. So differentiate term by term, so that's going to be 6x plus 6. Okay, so critical values, those come from the first derivative. Anywhere where the first derivative is 0, that means we have a horizontal tangent line. That's potentially a location where we could have a maximum or could have a minimum. So I'm going to take my first derivative, set it equal to 0. Okay. Now I notice that my coefficients have a common factor of 3. So to make my life a little bit easier, I'm going to go ahead and divide that out. So that's going to be x squared plus 2x minus 3 is equal to 0. I divide the 3 into 0 and it's still 0. So now I want to factor this. So I'm looking for numbers that multiply to give negative 3, that also add to give positive 2. And that's going to be a positive 3 and then a negative 1. Now once it's factored, I can set each factor equal to 0. So we know that x plus 3 could be 0. Or x minus 1 could be 0, which corresponds to critical values at negative 3 and at positive 1. Okay, well, I've kind of done things a little out of order here, so let's go down and let's use the second derivative test first in order to classify what we're looking at. Based on these critical values, does this represent a maximum or minimum? Does this represent a maximum or minimum? And then go from there. Okay, so at negative 3, x equals negative 3, which was one of our critical values, The question is, what is the value of the second derivative at that location? In other words, if we evaluate f double prime of negative 3, well, what's that value going to be? Well, I'm going to sub that into the formula for my second derivative. So that's going to be 6 times negative 3 plus 6, which is going to be negative 18 plus 6, which is going to be negative 12. But most important, it's less than 0. It doesn't matter that it's negative 12 versus negative 1 million. It matters that it's negative. So at this particular location, we have a negative second derivative. Well, if we have a negative second derivative, negative means concave down. Negative means concave down. Well, down is down like a frown. So that means at this location, at this critical value, our graph is going to have a shape like this. So if our graph is shaped like this at this particular value of x, which is again a critical value, a possible location for a maximum or minimum, that means that this critical value represents the location for a maximum. Now what about x equals 1? Same idea. We want to evaluate the second derivative at that location. So f double prime of 1 is equal to 6 times 1 plus 6. Well, 6 times 1 is 6. 6 plus 6 is positive 12. But again, I'm not worried about the fact that it's 12 specifically. I'm worried about the fact that it's a positive number. So if my second derivative is greater than 0, that means I am concave up like a cup. So that means the critical value at that location where we're concave up represents the location for a minimum. It's the lowest point based on the shape of the graph at that location. So those are going to be the locations for my extreme values, but what are the extreme values? What's going to be the highest value? What's going to be the lowest value based on the fact that this is the location for a maximum and this is the location for a minimum? Well, just like with the first derivative test, this is the moment where I need to go and I need to use the original function. If I'm looking for actual outputs associated with specific inputs, I've got to plug each of these into the original function. So f of negative 3 is going to be negative 3 cubed plus 3 times negative 3 squared minus 9 times negative 3 minus 13. And we can either evaluate it that way or we can type in our function. Let's do that here. Let's type that in and let's use the table. So I'm not typing in these specific values, I'm typing in the function since we do want to graph it with our graphing utility. So x cubed plus 3x squared minus 9x minus 13. And let's graph that. Okay, so there's our graph. We want the extreme values, so go to the table. So f of negative 3, well there's negative 3. The y value associated with that is 14. So f of negative 3 is going to be 14. F of positive 1, let's go to positive 1, has an associated y value of negative 18. So this is going to be the value of our relative maximum, and this is going to be the value of our relative minimum. And again, we can verify from the graph that this assessment makes sense. So let's zoom out just a little bit so we can see those peaks and valleys. There we go. Okay, so we see a peak to the left, we see a valley to the right. We know those locations are going to be associated with first derivative values of 0 since we have a flat horizontal tangent line at those locations. And we do see that the value on the left is going to be a peak, the value on the right is going to be a valley, hence maximum and minimum. Okay, let's do another example using our second derivative test. Okay, so let me get out of this graph real quick. There we go. Okay, so we want to use the second derivative test to find the relative extreme values for f of x is equal to 3x to the 5th power minus 20x cubed And then again, we want to sketch, get a sense of the picture using our graphing calculator. So start with our critical values, those possible locations for your maximum and minimum values, which means, of course, we have to find the first derivative to start with. So differentiating our function, we have 15x to the 4th power minus 60x squared. Okay, now we also need to find our second derivative if we're going to use the second derivative test. So differentiating the first derivative, we have 60x cubed minus 120x. That is our second derivative. Now the critical values occur wherever our first derivative is 0. So let's set that equal to 0. So 15x to the 4th minus 60x squared is equal to 0. Okay, now what can we not do? We cannot move this term over and divide out x squared, not allowed. You can never divide out and eliminate instances of the variable because you'll lose solutions to your equation. So this has to be factored. Now, we can start like we did before though and divide out any common constants. So 15 and 60 have a common factor of 15. So I'm going to divide that out just to make the problem a little bit simpler. So the 15 goes away, we divide 60 by 15, and that's going to be 4. And then 0 divided by 15 is just 0. Okay, so now we can solve this. Now we need to factor this. Okay, so start with the greatest common factor. We're looking for things that our two terms have in common. So the only thing they have in common is in terms of x. We have 4 x's and then 2 x's, so they have a total of 2 x's, or x squared, in common. And that leaves us with x squared minus 4. Okay, and once we factor out the greatest common factor, we need to look at what we're left with and see if we could go any further. This is a special case called a difference of squares, and it also factors. So first term is a perfect square, second term is a perfect square. We could think of this as x squared minus 2 squared, and that'll tell us how to factor it. So our full factorization is going to be x squared times x plus 2 times x minus 2. Again, based on how this is structured and the basic formula we have for factoring a difference of squares. So if we then set each of our factors equal to 0, x squared is equal to 0, x plus 2 is equal to 0, x minus 2 is equal to 0, we get x equals 0, x equals negative 2, and x equals positive 2. So those are going to be the locations for our critical values. Those are the possible locations of a relative maximum or a relative minimum. Okay, so again, let's use our second derivative test first, and then we'll go back and we'll look at the actual function values. So we want to evaluate the second derivative at each of these critical values to determine how the graph is going to be shaped at that location. Is it curved upward? Is it curved downward? That's going to determine whether or not these represent peaks or valleys or possibly none of the above. So first one, f double prime of, let's start smallest and work to largest, so negative 2. Okay, so let's look at our second derivative. So that's going to be 60 times negative 2 cubed minus 120 times negative 2. Okay, and let's just evaluate this one by typing it in. So 60 times negative 2 raised to the third power minus 120 times negative 2. Okay, we press enter, negative 240. Now, as before, I'm not worried about the fact that it's specifically negative 240. I'm worried about the fact that it's specifically less than 0. So less than 0, second derivative less than 0 means concave down, down like a frown. Okay, so if it's concave down like a frown, that means our critical value represents a maximum, highest point based on the curvature of the graph. Now what about our second derivative for our next critical value in order, which would be 0? So 60 times 0 cubed minus 120 times 0. Well, what happens when we sub in 0 in both of these locations? Notice this first term, 0 cubed, would be 0. Well, 0 times 60 is 0. 120 times 0 is 0. The whole thing evaluates to 0. So what happens there? Well, let's flip back over. If our derivative, second derivative, is less than 0, it's concave down, which means we have a maximum. If our second derivative is greater than 0, we're concave up, which means we have a minimum. What happens if it's equal to 0? Notice we don't have a classification there. What that means in this case is that the second derivative test is inconclusive. We can't actually classify this particular critical value just using the second derivative test. So in this case, because it's inconclusive, we're just going to determine from the graph. Once we go and look at the graph, we'll determine if this is an extreme value just based on what we see from our graph. So anytime the second derivative evaluates to 0, the second derivative test is inconclusive. Either you can use the first derivative test, or once you graph the function, you can just determine what you see at that location from the actual graph of the original function. Okay, and then let's do f double prime of positive 2. So that's going to be 60 times 2 cubed minus 120 times 2. Okay, and again, let's evaluate that in the calculator. So 60 times 2 cubed minus 120 times 2. And that's going to give us positive 240. But again, more importantly, it's just some number that's greater than 0. So if it's greater than 0, that means we're concave up like a cup, which means we've found the location for a relative minimum. Now, what about that one in the middle? Well, we want to type in and graph this anyway, and we're going to have to get the y values to get the extreme values anyway. So let's go ahead and type in our function to the graphing calculator, and we'll get both of those things at once. So I'm going to clear out what we just graphed. Now we want to graph the actual function. So 3x to the 5th power minus 20x cubed. Let's graph that. Now it's hard to see because we're zoomed out, so let's zoom in. Zoom into the center. Okay, let's see if we can go a little bit further. Let's go to zoom standard. Okay. This doesn't look right. Why does this not look right? Did I type the right thing? Let's double check that. Y equals 3x cubed minus 20x cubed. Oops. There's a reason it didn't look right. That should be 3x to the 5th power, right? There we go. Okay, that was not the graph we should see. That is the graph we should see. That makes more sense. Okay, apologies for that. Always double check what you type. Now, that makes sense because notice we have a peak up here. We've got another critical value where we have a horizontal tangent line, and then we've got a valley. And again, let's zoom back out just a little bit so we can get a better picture. And it's not great, but it's okay. So let's zoom back in a little bit. So what's happening there at x equals 0? Well, we do have a horizontal tangent, which is why that value popped up as a critical value. But what can we say based on what we see from the graph? Notice it's sloped downward to the left of that point, but it's also sloped downward to the right of that point. So we're decreasing to the left, we're also decreasing to the right, which means that doesn't actually represent an extreme value. So x equals 0, not an extreme value. So we can say based on the graph that it is neither a maximum nor a minimum. We don't get any special information from that particular graph or from that particular value for the second derivative, and from the graph we determine It's neither a maximum nor a minimum. Now, what about -2 and 2, which we did determine represent maximum and minimum values? Well, f of -2, we can determine from our table, now that I have the correct function typed. F of -2, we have an associated y value of 64. Okay, so based on our classification for that critical value, we know that is a maximum. So that is going to be the maximum function value associated in that general area. Now that does not mean it's the highest value on the function, but it's a maximum in relation to the x values and their associated y values around this particular location. Now f of +2, we decided that was a relative minimum. +2, -64. Okay, so we have a function value of -64. So that is the relative minimum. Again, not necessarily the lowest point on the graph, but the lowest in relation to the points around it, specifically a valley located on that graph. Okay, so we've done a couple of examples using the second derivative test to classify our extrema. Now let's talk about more just general explanation. What do we see from a graph based on the first derivative and the second derivative tests? So just as we can have critical points, critical values, there's also a corresponding concept from the standpoint of concavity. So critical values, critical points represent locations where we can change from increasing to decreasing or from decreasing to increasing. Well, what happens when we change concavity? Because there will also be locations where we change from being concave up to being concave down. These are what we call points of inflection. So changes in concavity are going to give us important information regarding a graph's shape. Just as locations for increasing and decreasing behavior give us information about shape, concavity gives us more specific information about shape. So a point where concavity changes, in other words, where our second derivative goes from positive to negative, or vice versa, this is what we call an inflection point. This is an inflection point. So what could an inflection point look like? Let's talk about that. Okay, all of these points that have been labeled represent an inflection point where we can change our concavity. So notice for this particular little snippet of this graph, we go from being concave down like a frown, which means the second derivative would be negative up to this point. And then at this point, it's neither curved downward nor curved upward. This is the point where the curvature changes. So we go from being curved down to being curved upward. So this is going to be the location for an inflection point. Now if we were to flip it, we go from an upward curvature to a downward curvature. Again, this also represents an inflection point. Now at this particular location, notice we would have a vertical tangent line at that particular location. But again, it represents a change in curvature. So we go from a downward curvature to an upward curvature. But what we would see from the derivatives at this per location is a little bit different. So for this particular function, it would be differentiable at all x values. This function would also be differentiable at all x values. We don't have any issues. But notice at this particular location on the graph of this function, because there is a vertical tangent line, it would not be differentiable at this particular value of x. So although this is a key point where things change on the graph, this is a location where the first derivative would be undefined, hence the second derivative would be undefined as well. So how do we find these points of inflection? Well, we find them in basically the same way that we find our critical values, our critical points, except we're using the second derivative rather than the first derivative. So if our function has a point of inflection, again, that's where the curvature changes, it must occur at a value that we'll call x sub 0, where one of the following criteria is met. So either the second derivative at that value of x is equal to 0. What does that mean? That just means the first derivative is not changing. We're not increasing the first derivative, we're not decreasing the first derivative, it's staying constant. Or it can occur at locations where f double prime of this value is undefined. And that is represented by that second graph. Again, why would the second derivative be undefined? It's undefined because the first derivative at that location is undefined. So once we end up with something that's not differentiable, in general, we won't have it be differentiable at that location when we take successive derivatives. So basically the same criteria for a critical point, but now we're talking about the second derivative rather than the first derivative. And again, these locations represent where the curvature for the graph changes, where we change from being either curved upward or downward to the other type of curvature. So let's do some practice finding these points of inflection, which are going to break our graph up into regions where we see different types of concavity. So just like we can classify a function as being increasing versus decreasing over an interval, we can classify the function as being concave up or concave down over an interval. Okay, so we want to find our points of inflection, the actual point, that means x value and y value, and the intervals of concavity, how we're curved across different intervals for this particular function. For f of x is equal to x cubed plus 3x squared minus 9x minus 13. Okay, so let's start with the inflection points. Think of those like critical values for the first derivative. So the inflection points are going to occur at locations where either the second derivative is 0 or where the second derivative is undefined. So in order to find the second derivative, we of course need the first derivative first. So differentiating one time, we have 3x squared plus 6x minus 9. And then if we take our second derivative, differentiate again, that's going to be 6x plus 6. That looks familiar, right? So inflection points are going to occur either where the second derivative is 0 or where it's undefined. Now, this second derivative is a polynomial function. Polynomial functions are defined at all values of x. So we're only worried about the first criterion in this case. So we're going to take our second derivative, set it equal to 0, solve for x, and we're going to get x is equal to -1. So that is going to be the location for a point of inflection. So let's put that on the sign chart. Now we're going to do basically the same thing here that we did with our critical values, but now we're analyzing the concavity. We're not focused on what happens with the first derivative. We're focused on what happens with the second derivative. So let's pick a value on either side of this x value, and because our second derivative is so easy, there's no need to really use the graphing utility here. We can just do this by hand. So we want to pick a test value in either side of this location where supposedly our concavity is changing. And based on what we see for our test value, that represents the interval as a whole and the curvature we see as a whole. So something less than -1, maybe -2, something greater than -1, maybe 0. Now what are we checking? We're checking concavity, which is represented by our second derivative. So we want to evaluate our second derivative at both of these locations. So f double prime of -2, and we can do this by hand. F double prime is really simple. So 6 times -2 plus 6. So 6 times -2 is -12. -12 plus 6 is -6, which is less than 0. So the interval from -infinity to -1, the second derivative is less than 0. Less than 0 means concave down, down like a frown. So we are concave down over that interval. Now, the next one, from -infinity to, -1 to infinity, getting ahead of myself. We're evaluating at 0. So f double prime of our test value, 0. Sub it into the second derivative. So 6 times 0 plus 6. This term's going to go to 0, which means it's going to be 6, but more importantly, it's going to be positive. So if our second derivative has a positive value, positive means concave up like a cup. So our graph is concave up over the interval from -1 to infinity. And our graph is concave down over the interval from -infinity to -1. And then last but not least, let's find the actual point, the actual coordinates where this change in concavity occurs. So we know the point of inflection occurs at x equals -1. Well, what's the y value to go with that so we have the actual point? Well, we need f of -1. So sub in a -1. So -1 cubed plus 3 times -1 squared minus 9 times -1 minus 13. Let's just evaluate this by plugging it in. So we have -1 cubed plus 3 times -1 squared minus 9 times -1 minus 13. And you're probably looking at this and thinking, I could do this by hand. Yes, you could do this by hand. This one's not too bad. And that's going to give us a -2. So that means our actual point of inflection is the point -1, -2. So that's going to be the location on our graph. To the left of that, we're concave down. To the right of that, we are concave up. So that's the point where our concavity changes. Okay, let's try another example like this one. So again, we want to find our points of inflection, find the intervals of concavity. And you'll notice this function and the last function, they're the ones we already looked at in terms of classifying our maximum and minimum values. We're just looking at them from a slightly different point of view now. So we've got our function, f of x is equal to 3x to the 5th minus 20x cubed, the one that I apparently couldn't graph correctly. We want to find its inflection points, the points where the concavity changes, concave up to concave down, or vice versa. So in order to find the locations where our concavity changes, we need to find the second derivative, but we've got to find the first derivative first. So that's going to be 15x to the 4th power minus 60x squared. And then if we differentiate again, we have 60x cubed minus 120x. Okay, so a point of inflection will occur either where this is 0 or where it's undefined. Again, this is polynomial, so it's defined for all values of x, which means we're just looking for locations where this has a value of 0. So let's take this and set it equal to 0. Okay. Now again, we don't want to ever divide out our variable, because anytime we divide out the variable, we eliminate possible solutions to our equation. But we can divide out common factors for our coefficients. So 60 and 120 have a factor of 60 in common, so we can divide that out on both sides, which will leave us with x cubed minus 2x, and then 0 divided by 60 is still 0. And now we want to factor what we're left with. So the greatest common factor between our two terms is going to be x, and we're left with x squared minus 2. Now, because 2 is not a perfect square, it's going to be more difficult to factor this using the difference of squares formula. So I would go ahead and split this up and set each of these factors equal to 0. So x is equal to 0, which means we don't have to do anything. We've already found that value. And then x squared minus 2 is equal to 0. Now here, because we only see one instance of the variable, we can isolate our x. So add the 2, move it over. So we have x squared is equal to 2. And then we take the square root of both sides. Now, the rule here, the square root property says if we take the square root of both sides, we do need to add a plus or minus on one side to indicate that we could square both a positive and a negative number and give us an output of 2. So we take the square root, but we also need that plus or minus. So this represents two numbers. This represents x equals the negative square root of 2 and x equals the positive square root of 2. So these three x values, notice one of them is rational, two of them are irrational. These represent the locations where we have points of inflection. So we'll find the actual associated y values in a moment. Let's just look at concavity right now. So we have three different locations where our concavity changes. So put 3 marks here on the sign chart. So smallest to largest, negative root 2, 0, then positive root 2. Again, I'm going to box them in so that we don't confuse any numbers that we might put here. Okay, now to save ourselves a little bit of time, let's do kind of what we did before. If you'll remember, when we were looking for intervals where things were increasing and decreasing, we could analyze that using the graph. So let's see what we can see from the graph of the second derivative. Where is the second derivative going to be positive? Where is it going to be negative? So let's go in and let's graph our second derivative. So that's going to be 60 times x raised to the third power minus 120 times x. So there's the function representing our second derivative. Let's graph that. Okay. Now, these locations where we've crossed in between tick marks along the x-axis, those represent that negative and positive root 2. What we're focused on is what are the signs around either of these locations. So let's zoom in on each of these locations and see what's going on. So I'm going to arrow over. I'm going to focus on that leftmost intercept. Okay, so at that leftmost intercept, we want to analyze what's happening to the left of that, what's happening to the right of that. What's the sign to the left, what's the sign to the right? Well, to the left of that, notice we're going to be below the x-axis. So for x values that are less than negative root 2, we know that the second derivative is going to be negative. Now, as we go from the left to the right, we go from a negative second derivative to a positive second derivative. So we go to a location where the second derivative is greater than 0. Now, when we get to 0, it almost looks vertical. It's not quite, okay? It's still slightly diagonal, but notice to the left, we're above, and as we transition through x equals 0, we're now below. So to the left, again, our second derivative is greater than 0, and to the right, our second derivative is less than 0. Okay, now let's zoom back out. And let's just zoom standard. Let's zoom standard first. There we go. Okay, we can probably see enough just from this zoomed point. So if we analyze what's going on over there with our last location where our second derivative had a value of 0, to the left of that, we're negative. To the right of that, we're positive. So to the left of root 2, our second derivative is negative. To the right, our second derivative is positive. Well, once we know that, we know enough to evaluate the concavity for this function. Now keep in mind, the graph we're looking at is not the graph of the function, it's the graph of the second derivative. The second derivative tells us how the original function will be curved when we look at its graph. So anywhere where the second derivative is negative, we are curved downward. Anywhere where the second derivative is positive, we're curved upward. And anywhere where the second derivative is 0, that's our inflection point. That's where the curvature changes. So where we are negative, our second derivative is negative, we're concave down. So we have two intervals where our function will be concave down. And then the two intervals where our second derivative is greater than 0, we are concave up. Now notice these are broken apart at negative root 2, 0, and positive root 2. So let's label our infinities, and then we can write our intervals, and we'll go back and look at those inflection points. So we're concave up over two intervals. So from negative root 2 to 0, that's one interval. Just like in classifying increasing and decreasing intervals, we don't use brackets, we use parentheses, because at those individual values they're breaking apart our intervals. Different things are going on. We're neither increasing nor decreasing. We're neither concave up nor concave down. So we are concave up over the interval from negative root 2 to 0, and then also from root 2 to infinity. And then we are concave down from negative infinity to negative root 2, and then also from 0 to the square root of 2. Notice if I were to join all of these intervals together, I go from negative infinity to negative root 2 to 0, 0 to root 2 to infinity. So in other words, I've classified the whole real number line, the whole domain for the function, and then the intervals are split up around those locations where we know we have a point of inflection. So we have our concavity for this graph classified. We'll look at the graph in just a moment. Now let's find the actual coordinates for the points of inflection. Now because our x values are a little bit more complicated, specifically the negative root 2 and the root 2, evaluating here is going to be a little bit more complicated as well. So we're going to take our time. We're going to do this really slowly. So let's start with the easy one. Let's start with 0. So f of 0. This one's pretty easy to evaluate. 3 times 0 to the 5th minus 20 times 0 cubed. We'll notice both of these terms go to 0. So that's going to be 0, which means the point of inflection has an x coordinate of 0 and a y coordinate of 0. Okay, now what about the other ones? Let's do the positive square root first. So positive square root of 2. So we're going to sub it in. So 3 times the square root of 2 raised to the 5th power minus 20 times the square root of 2 raised to the 3rd power. Okay, now what happens if we take something like the square root of 2 and raise it to the 5th power? Let's see what would happen in the calculator. So the square root of 2, okay, and then we are raising it to the 5th power. What's going to happen if I press enter? Okay, I'm going to get a decimal. Well, remember, I can normally convert a decimal to a fraction. So let's see what happens if I try to do that. Well, notice it doesn't do anything. The reason it doesn't do anything is because the square root of 2 raised to the 5th power is still an irrational number. Irrational means it can't be written as a fraction. So that means your calculator is not going to be as helpful as you might like in this situation. So you're going to have to use what you know about radicals and exponents to simplify this and write it in an exact form. Now, of course, we can check and make sure our simplification is correct using what we know about this approximation from the calculator. So root 2 raised to the 5th power. Well, first off, what would happen if we took the square root of 2 and squared it? You probably know the answer to that, but let's just see that in the calculator. So if we took the square root of 2 and squared it, we would get 2. Well, if we took the square root of 2 and cubed it, we'd be in a similar situation to taking the square root of 2 and raising it to the 5th power. What if we took the square root of 2 and raised it to the 4th power? What would happen then? That would give us 4. Why does it give us 4? Well, the square root of 2 to the 4th power is the same thing as taking the square root of 2 and squaring it, and then squaring it again. So here's the idea for what we're going to do. We know that raising it to the 5th power would be the same thing as raising it to the 4th power, and then multiplying by another square root of 2. How does that help us? Well, it helps us because the square root of 2 to the 4th power, as we determined on the calculator, is a rational number. So although we're left over with the square root of 2, this portion of that expression simplifies to something rational. And a similar kind of thing happens over here. So the square root of 2 cubed, well, if you were to plug that into the calculator, you're going to get another nasty decimal. But we know that that would be the same thing as the square root of 2 squared, and then multiplied by another square root of 2. So we can simplify the parts with the even exponents and then just leave that additional square root of 2 attached to it. So square root of 2 raised to the 4th power, we just determined that that's 4. So 3 times 4 is going to be 12. That's going to be 12 times the square root of 2 minus square root of 2 squared, which we determined was 2. 20 times 2 is going to be 40. So minus 40 times the square root of 2. Well, if we have 12 square roots of 2 and we subtract 40 square roots of 2, forget about the fact that these are root 2. Think if they were just x, like 12x minus 40x. It's just a combining like terms kind of thing. So that's going to give us negative 28 times the square root of 2. So that means our inflection point is going to be square root of 2, negative 28 square root of 2. Now, how can we check and make sure that this worked out? Because there was quite a bit of algebra going on here. How can we verify that this is, in fact, correct? Well, first off, what is negative 28 times the square root of 2? Let's plug that in. Now, we're going to get an irrational number. That's okay. That's our approximation. So about negative 39.6. What do we get if we just evaluate the expression we have right here at the very beginning before we began simplifying? Let's see what that is. So 3 times the square root of 2. Oops. Let me delete that. Delete. There we go. You want to get out of the radical before you close your parentheses. That's raised to the 5th power. Reading too low. Minus 20 times the square root of 2. Again, make sure you arrow out of the radical before you close your parentheses. And then that's raised to the 3rd power. Let me double check that. 3 root 2 to the 5th minus 20 root 2 cubed. Okay? What's going to happen when you press enter? What do you think is going to happen? Well, there you go. You get them and they match. Why do they match? Well, we're saying that these are equivalent. We simplified this more complicated expression down to negative 28 root 2. So they should evaluate to the same approximation in the calculator. And that is a confirmation that our evaluation, our simplification is correct. So although the calculator is not going to do the heavy lifting for you there, it will at least allow you to check your answer. And then last but not least, let's find the inflection point associated with x equals negative root 2. So it's basically going to look like what we just did, except we now have to take the negative into consideration in terms of what the exponents are going to do to that sign. The rest of it, though, in terms of breaking apart the exponents, that we can just do the same way we did before. Okay, so let's focus on the exponent and the negative first. We can apply the exponents to the negative and to the radical separately. So if we raise a negative to an odd power, the general rule is that it'll stay negative. So a negative to the 5th power, think of it as just raising a negative 1 to the 5th power. It's still going to be negative. So that's going to make this whole term negative. So that's going to be the same thing as negative 3 times the square root of 2 to the 5th power. In other words, just take care of it ahead of time. Now for the next one, negative root 2 to the 3rd. Again, think of this like a negative 1. Negative 1 cubed is still going to be negative. So that'll flip our sign here. So the term itself was negative, but when we take this negative 1 and cube it, it remains negative. So that double negative is going to combine and turn this term positive. So plus root 2 cubed. Okay, and we already determined what happened with root 2 to the 5th power and with root 2 to the 3rd power. But just to be thorough, we have negative 3, and then we break this down into root 2 to the 4th power times that extra square root of 2 plus 20 times root 2 squared times that extra square root of 2. Okay, so root 2 to the 4th power, we determined that was going to be 4. In other words, square root of 2 squared, which gives you 2, and then square that again, which gives you 4. So combining with that negative 3, that's going to be negative 12 times that leftover square root of 2 plus square root of 2 squared, which is 2. 2 times 20 is 40. So 40 times that leftover square root of 2. And then we combine those together. Notice it's almost the same terms, but the signs have flipped. So negative 12 plus 40 is going to be positive 28 square root of 2. So our third and final inflection point will be negative square root of 2, positive 28 root 2. And again, let's check this in the calculator. So we want to evaluate 28 times, well, we don't need that, times the square root of 2. Here we go, enter. Okay, is that going to be the same thing as what we have as we originally evaluated just by substituting in negative square root of 2? Well, let's double check. Make sure you're careful with your parentheses here. So your parentheses need to go around both the negative and the radical, and you need to get out of the radical before you close your parentheses. It will make a difference. Okay, minus 20. What did I just do? Let's go back. There we go. Minus 20 times the negative, what am I doing here? Negative, there we go. Getting ahead of myself. Square root of 2, close your parentheses, and then raise it to the 3rd power. Let me double check. So 3 negative root 2 to the 5th minus 20 negative root 2 to the 3rd. And there we go. Good. After much ado, finally typed it in. So our approximations are the same. So again, that's confirmation that our simplification does make sense. So our 3 inflection points, just to highlight where they are, there's point 1, there's point 2, and there's point 3. So again, those represent the locations where our concavity changes, where we change from being curved upward to curved downward or vice versa. Okay, let's take one more example and let's put it all together. So everything we talked about with the first derivative test, determining where our function is increasing and decreasing, what we determined from our second derivative tests, where our function is concave up, where it's concave down, basically classifying everything we can about this function and its graph using what we know about the first and the second derivative. Now, in terms of classifying the extreme values, you can do that one of two ways. You can use the first derivative test, you can use the second derivative test. You're going to get the same classifications either way, so it's really just up to you what you prefer to do. If anything, you might want to double check it by doing it both ways. Whatever the first derivative test tells you, the second derivative test should confirm that. Okay, either way, we have to start at the same location. So relative extreme values, okay, that's related to our critical values. Remember, those come from the first derivative. Increasing and decreasing intervals, also related to the first derivative, wherever it's positive. So let's write down what we know about this. Wherever the first derivative is greater than 0, we are increasing. Wherever the first derivative is less than 0, we are decreasing. Points of inflection, remember those occur in locations where our second derivative is 0 or undefined. So critical values, that's where the first derivative is 0. Locations for our points of inflection, that's where the second derivative is 0. And then also the intervals of concavity. So whenever our second derivative is greater than 0, we're concave up. Wherever our second derivative is less than 0, we're concave down. Now, either case, we just need to start with the derivative. So first derivative, okay, differentiate using the power rule. So 4x cubed minus 4x. And then I know I'm going to need the second derivative down here, so let's go ahead and take the second derivative as well in order to get those points of inflection, the intervals for concavity. Okay, Okay, so we're differentiating our first derivative. So that's going to be 12x squared minus 4. Okay, so what does the first derivative tell us? It tells us where we have critical values, and then based on how the sign changes around those critical values, it tells us where our graph is increasing and where our graph is decreasing. Okay, so this particular expression is defined for all values of x, so we're just looking for locations where this would be equal to 0. So 4x cubed minus 4x is equal to 0. We can divide out that common factor of 4. It doesn't affect our solutions. So x cubed minus x still equal to 0. Now we need to factor. We have a common factor of x between these two terms. So x times x squared minus 1 is equal to 0. Now again, this is a difference of squares, so 1 is the same thing as 1 squared. So that's going to be x times x plus 1 times x minus 1, which means our critical values occur at -1, 0, and 1. So those are the potential locations for a relative maximum or a relative minimum. Now we want to find these values, but we also want to classify the different intervals of our graph as locations where we're increasing or decreasing. So let's go ahead and do the sign chart, and let's just analyze what we see on these intervals. So placing our critical values on here, -1, 0, and 1, -1, 0, and 1. Okay, and again, this is a great time to use the graphing function in your graphing calculator. Okay, but so let's graph the derivative rather than the original function. We want to know, where is this derivative going to be positive and where is it going to be negative. Okay, so there's the function representing our derivative. We graph that. Okay, and we see those 3 locations where the derivative is 0. So those locations where the derivative crosses the x-axis, that's -1, 0, and 1. Those are the locations of our critical values. So what's happening on either side of those? Well, let's zoom in just so we're sure. Zoom in where it's centered. Okay, so they're at our first critical value at -1. Okay, to the left of -1, our derivative is negative because the graph is below the x-axis. So over here, our first derivative is less than 0. Now as we cross over at x equals -1, go from -1 to 0, we're above the x-axis. So our first derivative is greater than 0. Once we get to 0, we cross over again to below the x-axis. So our first derivative is less than 0. And again, when we get to 1, we cross over again. So our first derivative is greater than 0. Let me get out of the graph. Okay, so what does this tell me about the graph of the original function? Well, wherever my first derivative is negative, where it's less than 0, my function is decreasing. And then wherever my first derivative is positive, my function is increasing. So based on the fact that we change behavior at each of our 3 critical values, that means these do represent locations for either a maximum or a minimum. So if we go from decreasing to increasing, that means we've hit a valley. That means we have a minimum at this location. Increasing to decreasing, we've hit a peak, which means we have a maximum. And then decreasing to increasing, again, we've hit a valley, which means we have a minimum. So let's classify our intervals, and then we'll find the associated y values to go with each of these. So we are increasing on the intervals from -1 to 0, and then also from 1 to positive infinity. So -1 to 0, and then also positive 1 to infinity. And we are decreasing on the interval from negative infinity to -1. and then also on the interval from 0 to 1. And again, a good way to double check that you've covered everything, you should be able to transition across the whole number line, jumping from interval to interval. So negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to infinity. We go all the way from one infinity to another. Okay, so that classifies essentially the slope across our graph. Are we sloped upward? Are we sloped downward? Now we want to define the actual minimum and maximum values. So let's find those. So we want the function value associated with each of these critical values. We know we can do this by hand if we want. We can also do this using the graphing utility in our calculator. Now this one you might be able to do in your head realistically, but let's just type this one in. These aren't too bad based on the fact that we have a pretty simple function. So negative 1 raised to the 4th power minus 2 times negative 1 squared. And that's going to give us an output of negative 1. So when x is negative 1, y is also negative 1, and that's going to be a relative minimum. Now when we substitute in 0, 0 to the 4th power is 0, 0 squared is 0, the whole thing evaluates to 0, so just 0, 0, which is a relative maximum. Now you may be thinking you get an output of 0, how can that be a maximum? It just means it's higher than the other points around it. It doesn't mean it's the highest point on the graph. It doesn't mean we don't have higher points on the graph. It just means this is a peak in relation to the points that are around it near that particular location on the graph. And then if we evaluate at positive 1, 1 raised to the 4th power minus 2 times 1 squared. And that's also going to give us negative 1. So when x is positive 1, we also get a y value of negative 1. And again, that is a relative minimum value. Let's verify that from the graph. So let's go ahead and put the graph of the function in, and then we'll look at its concavity. So x raised to the 4th power minus 2x squared. And there's our graph. So we can see where we have a valley, where we have a peak, where we have a valley, and it is associated with the x values at negative 1, 0, and 1. Now what can we see about concavity? We're looking for areas where we're curved down and areas where we're curved upward. So it looks like we change concavity about halfway between negative 1 and 0 and about halfway between 0 and 1. So on the left-hand side of the graph, we're curved upward, and then as we get closer and closer to 0, going from negative 1 to 0, we're curved downward, and then we go back to being curved upward. So it looks like more than likely we have 2 inflection points where that concavity is going to change, which is then going to break our graph into 3 intervals with respect to concavity, where we change behavior. Okay, so let's verify this algebraically. Oops, what am I doing? Second mode, there we go. Okay, so we want to find our points of inflection and then the associated intervals of concavity broken up around those points. So our points of inflection are going to occur where our second derivative is equal to 0. Okay, now here we only have one instance of our variable, which means we can just isolate that. So add 4, move it over. So 12x squared is equal to 4. We're going to divide by 12. So x squared is equal to 4 over 12, which reduces to 1/3. And then we need to take the square root of both sides. Now remember, when you take a square root in an equation, you need your plus minus. So square root of 1/3. Now there's a rule with radicals that says if we take the radical of a quotient, we can split that up and take the square root of the numerator and the square root of the denominator separately. Well, how does that benefit us? We can't do anything with the square root of 3, but we can simplify the square root of 1 to just a 1. And so that's going to be 1 over the square root of 3. In some instances, we'll want to rationalize that. So if we wanted to rationalize that, we could multiply that by root 3 over 3 on the top and bottom. The idea with rationalization is we don't want to have an irrational number in the denominator. And so by multiplying on top and bottom by the radical we want to eliminate, we end up with something that's rational. So either one of these would be fine. We'll just stick with the non-rationalized version because we're not really going to need the rationalization. But just a heads up, sometimes that is a preferred form. Okay, so those two values, notice that's two values, one's negative, one's positive, those represent the locations where we change concavity. So just like we had a sign chart for our first derivative, let's do a sign chart for our second derivative. So negative 1 over root 3, and then positive 1 over root 3. Okay, and just like we use the graph of the derivative, we can use the graph of the second derivative to save us a little bit of time here in analyzing this function. So let's type in our second derivative. So 12x squared minus 4, and let's graph that. Okay, so what are we analyzing? This is the graph of the second derivative. We want to know where is our second derivative positive and where is it negative. Well, what's significant about the x-intercepts here? Those are the locations where our second derivative evaluated to 0. So that's going to be negative 1 over root 3 and positive 1 over root 3. Those are your x-intercepts there on this graph. So to the left of the first intercept, notice we're above the x-axis, which means that the value of our second derivative is going to be greater than 0. Now once we hit that first intercept, again where our second derivative was equal to 0, notice we jump from above the x-axis to below, which means our second derivative goes from being positive to being negative. And then when we get to our next intercept, we jump from below the x-axis to being above, which means our second derivative is then greater than 0. So don't focus on this from the standpoint of increasing or decreasing. Don't focus on this from the standpoint of how the original graph is shaped. We're just using it to analyze the signs of our particular derivative. Based on the signs, that's going to tell us what our concavity looks like. So anytime our second derivative is greater than 0, we're concave up. So up like a cup. So we have two intervals where that occurs. And there in the middle, our second derivative is negative, which means we are concave down. Okay, so we have two intervals over which we're concave up. So here's negative infinity, here's positive infinity. So negative infinity to negative 1 over root 3, we are concave up. And then also from positive 1 over root 3 to positive infinity. And then in between these two locations, that's where we're concave down. So negative 1 over the square root of 3 to positive 1 over the square root of 3. And there we go. Okay, now what about our points of inflection? We know these are the locations where the concavity changes. What's the actual point on the graph associated with that change? Okay, so we're going to take these two x values, substitute them into our original function. Remember, we're always going to sub in here whenever we want to get actual points that are going to be on the graph. So f of negative 1 over root 3 is going to be the same thing as, if we sub in, negative 1 over root 3 raised to the 4th power minus 2 times negative 1 over root 3 squared. Now seeing this, you may think back to one of the previous examples we did where we couldn't evaluate anything with that square root in the calculator because the result was still irrational. Notice here though we have a square root, and each time these are being raised to even powers. Anytime we take a square root and raise it to an even power, the result will be a rational number. So I want to show you what's going to happen if you plug this in. This is different. Even powers versus odd powers, those do completely different things to our radicals. So here, something different is going to happen when we substitute in our values. Okay, minus 2, negative 1 divided by the square root of 3. Okay, and that is then raised to the second power. So double check you type what you wanted. Okay, once that's good, press enter. Okay, now again, notice we have a decimal. Let's see what happens when we convert this to a fraction. We'll notice that one actually converts because the result of this particular expression is rational. So that's going to be negative 5 over 9. So that means our inflection point is negative 1 root 3, 1 over root 3, excuse me, and then negative 5 over 9. Okay, now what about evaluation with positive 1 over root 3? Well, before I plug it in, let's think back to what happened here. What happened to the negative? If I raise a negative to the 4th power, what's going to happen? Well, it's going to go positive. Anytime we take a negative and raise it to an even power, the result is a positive number. Now, same thing here. We take a negative 1 and we square it. The result is a positive number. So the fact that this was negative 1 over root 3 didn't have any effect. It would have been the same thing if it had been positive 1 over root 3, just based on the fact that even exponents will take negatives and make them positive. So what that means is if we were to sub in the positive version of this original input, it's going to have the same effect. We're going to have the same output. So we can still do that again if we want, but as long as we recognize this relationship between negatives and these two exponents, we'll recognize that we're going to get the same output. The negative versus not having a negative is not going to make a difference here. So we also have an inflection point with positive 1 root 3 and the same associated y value. So those are going to be our inflection points. So a lot of things going on here, But essentially this would give us any information we would need to graph this function. We know where we have peaks and valleys based on those extreme values, those relative max and minimum values. We know where the curvature on our graph changes, where we change from being concave up to being concave down. And so realistically, we have anything we would need to be able to get a pretty accurate graph for this function. So to wrap up, let's look at an example similar to what we did in the last section, graphing based on what we know about our derivatives, in this case the second derivative, and some concavity. Okay, so we want to sketch a graph that follows these particular stipulations, these particular descriptions. Okay, now as before, when we did this before, keep in mind there are a variety of graphs that will satisfy these particular requirements. As long as we have a graph that meets these requirements, it can vary based on the actual graph, things like that. So we know that f of x is concave up at this particular location. Now be careful, we're not saying it's concave up across this interval. This is an ordered pair because it's at this specific location. So at the point 1, negative 3, which would be right here, I'm going to put that on the graph, at that particular location we are concave up. So up like a cup at that particular location. Now we are concave down at 8, 7. So that tells us that another point on this graph where we see some specific behavior is at 8, 7. Okay, so concave down, down like a frown at that location. And we have an inflection point at 5, 4. So 5, 1, 2, 3, 4. What does that mean? That means that's where we change our concavity. So we go from being concave up to concave down, and the transition is right there. So at that particular location, we're neither concave up nor we're concave down. That's where we transition. So at this particular location, concave up. Now it doesn't necessarily mean that this is the valley. It just means that we go through that particular location with an upward curvature. but if it makes more sense to you to have that be the valley of your graph, that's fine. So we're concave up at this location, so maybe we have something like this, and then concave up. Now we change our curvature here, which means we continue to be concave up until we get right there, and that is exactly where the concavity changes. That's where we change from concave up to concave down. So that's the transition point. So we have to be careful. That's where we suddenly transition to being concave down. So you see I'm using pen. I would encourage you to do these with pencil, particularly as you're starting to learn in general what these shapes look like. Do it with pencil because you're probably going to have to erase, make some changes here and there, and that's perfectly fine. So we're concave up through this point. We have an inflection point here where our concavity changes from upward to downward concavity, and then we're concave down at this location at the 0.87. So now that we have these two derivative tests, we've got a lot of resources to help us find maximum and minimum values. Now the one thing we do need to keep in mind is that the term maximum and minimum so far has been qualified with the word relative. It's a relative maximum and minimum value. So for instance, just looking at this graph, this would represent a relative minimum, but notice based on how the graph continues, based on this arrow, it still would continue down towards negative infinity. So although this is a valley on the graph, it does not necessarily represent the lowest point on the graph because we continue down towards negative infinity. Same thing here, this would represent a relative maximum, but it is certainly not the highest point on the graph, even based on what we can see. So the first and second derivative tests, they will give us information about these peaks and these valleys, but it's peaks and valleys in relation to the points around that particular location. So in terms of finding truly the highest point or truly the lowest point on the graph, we'll use the strategies we've talked about in these two sections, but we're going to have to go a little bit further. So rather than talking about relative maximum and minimum values, we're going to refer to absolute maximum and minimum values. The absolute highest, the absolute lowest points. We'll use our derivative tests. We'll add on a little bit from there.